Introduction to Hypothesis Testing, Part 2. In the first part of this video, we have demonstrated that in order to reject the null hypothesis, our sample mean should exceed the cutoff point and enter into the rejection region. The next question is, how do we calculate for this value? Before proceeding, we should take note that the decision rule set up for the Morgan Lane example is classified as an upper one-tailed test. A one-tailed test is a hypothesis test in which the entire rejection region is located in one of the tails of the sampling distribution. In one-tailed test, the entire alpha level is located either on the upper region or on the lower region of the distribution. The other type of test is the two-tailed test. It is a hypothesis test in which the entire rejection region is split into two tails of the sampling distribution. In a two-tailed test, the alpha level is split evenly between the two rejection regions. We will have an example of this in the succeeding videos. Going back to the Morgan Lane real estate problem, suppose the managing partners decided that they are willing to incur a 0.1 probability of committing a type 1 error. Assume also that the population standard deviation for closing is 3 days and the sample size is 64 homes. Given that the sample size is large and that the population standard deviation is known, we can state the critical value in two ways. First, we can establish the critical value as a z value. If the rejection region on the upper end of the sampling distribution has an area of 0.1, the critical z value from the standard normal table, a one-tailed test using a 0.1 alpha would be 1.28. This means if the sample mean lies more than 1.28 standard deviation above 25 days, the null hypothesis should be rejected. Otherwise, we will not reject the null hypothesis. For a much comprehensible comparison, we can also express the critical value in the same units as the sample mean, denoted by the x-bar sub alpha. We can calculate this value using equation 9.1, where the mu is the hypothesized value for the population mean, and z sub alpha is the critical value from the standard normal distribution. This equation can be used if the population standard deviation is known in advance. Applying equation 9.1, we determine the value for x bar sub alpha as follows. Substituting 25 for the population mean, 1.28 for the z value, 3 for the population standard deviation, and 64 for the sample size, we get a value of 25.48. A sample mean greater than this value, such as 26 days, will lead us into a conclusion to reject the null hypothesis. Alternatively, we can rearrange the previous equation into this equation, 9.2, so that we can calculate for a z value, which we will then use to compare to the critical z value. Our decision rule would be to reject HO if the computed z value is greater than the critical z value at 0.1 alpha. If not, we do not reject HO. Suppose the sample mean is 26 days, applying equation 8.2 would give us a z value of 2.67, which we will then compare to the 1.28 critical z-value at 0.1 alpha. And based on our decision rule, these would lead us again to a conclusion of rejecting the null hypothesis. Comparing the two approaches, the critical sample mean x bar sub alpha and the z-test statistics, both of them yielded to the same conclusion, as they should always will. The z-test is most commonly used in academic applications, while the critical sample mean approach is more suitable in business applications. Let us see another example. Mountain States Surgery Center. The center performs many knee replacement surgery procedures each year. Recently, research physicians at Mountain States have developed a surgery process they believe will reduce the average patient recovery time. The hospital board will not recommend the new procedure until there is substantial evidence to suggest that it is better than the existing procedure. Records indicate that the current mean recovery rate for the standard procedure is 142 days, with a standard deviation of 15 days. To test whether the new procedure actually results in a lower mean recovery time, the procedure was performed on a random sample of 36 patients. Step number 1, we need to specify the population parameter of interest. In our problem, we are interested in the mean recovery time. Step number 2, formulate the null and alternative hypothesis. For the null hypothesis, it would be greater than or equal to 142 because it is the status quo. The alternative hypothesis would be if less than 142. Step number 3, we need to specify the desired significance level. Suppose the researchers wish to test the hypothesis using a 0.05 level of significance. Step number 5, we then compute the test statistics. For this example, we will use the z-statistic approach. We would also assume that the sample mean computed is 140.2 days. Then, using the equation, we will have a z-value of negative 0.72. This is an example of a lower one-tailed test, since the rejection region lies on the left of the distribution. After computing for the z-value, we then need to know the critical z-value, which can be found from the table. One-tailed test using a 0.05 alpha, we then get a critical z-value of 1.6449 or round up to 1.645. Step number 6, we need to reach to a decision. If the computed z-value is less than the z-critical value, we need to reject HO. Take note that since this is a lower one-tailed test, the critical z-value has a negative sign. After computing for the z-value, which is negative 0.72, we found out that it is greater than the z-critical value, negative 1.645. Therefore, we do not reject HO. This means that there is no sufficient evidence to conclude that the new knee replacement procedure results in a shorter average recovery period. Thus, Mountain States will not be able to recommend a new procedure on the grounds that it reduces recovery time.